So welcome to lecture 6. So in this lecture we'll talk about sampling distributions. So in this lecture we'll discuss what is simple random sampling, sampling distribution, distribution of a sample mean, central limit theorem, and distance distribution between two means, and distribution of sample proportion, and finally distribution of difference between the two proportions. So let's start with the introduction. So we discussed the two parameters that we generally need to describe any given distribution. We call them parameters, are the numerical descriptive measures of population. So the two measures that we use for normal distribution is mu and sigma. So if you know mu and sigma, you can describe the entire distribution. So there is one parameter for a binomial distribution. So the binomial distribution requires p. So you just need to know what is the probability of each trial. So often these values of the parameters that specify the exact form of distribution are generally unknown. So we rely on the sample to learn about these parameters. Remember that we are taking a big set of population. So this is a big chunk of data, but we only take some part of it. So this part is what we use to analyze the data. So we call that the sample. So what is simple random sampling then? So the sampling plan or the experimental design determines the amount of information that you can extract, often allows you to measure the reliability of your inference. So reliability here refers to how good is your guess, or how good is the guess close to the original value. So that is the idea behind simple random sampling. So your sampling should be in such a way that the information that you extract will allow you to reliably measure the whole of the population. So simple random sampling is a method of sampling where we have the sample of size n of an equal probability being selected. For example, let's say if there are 4 boxes, then what is simple random sampling is that if the probability of selecting each box is the same, we call that simple random sampling. Here there are 4 boxes, so all boxes have a probability of 1 by 4 of being selected. So this process is basically called random sampling. So if you have bias, it means that any one of the boxes might be 2 by 4 and one another might be 0. This is the case where you might see, so this is an example of bias. So bias is where you favor one box over the another boxes. So this is the idea behind simple random sampling and how to make sure that the samples you take have the same probability throughout the entire sample size. Now, sampling distribution is basically the numerical descriptive measures calculated from the sample are generally called statistics, and these statistics generally vary from sample to sample. So that's why we give the name random variables. So this variability between this variability we call it as sampling variability, and the probability distribution of these statistics is called sampling distribution. So why do we need sampling distribution? So what is sampling distribution first? So the distribution of all possible values that can be assumed by some statistic and computed from samples of the same size randomly drawn from the same population is called as the sampling distribution of that particular statistic. So remember, the question is that there are mainly 3 phrases that you are looking at here. Number 1 is the distribution of all possible values that can be assumed by some statistic and computed from samples of the sample size randomly drawn from the same population is called as the sampling distribution of that statistic. So sampling distributions are important because they help in understanding statistical inference, how to make decisions. So probability distributions permit us to answer questions about sampling, and they also provide the foundation for statistical inference procedures. So this is a little bit of a higher statistical field, but as of now, just remember that whenever we are choosing a sampling distributions, we are choosing them because they give reliable results. Now, how do you construct a sampling distribution? So we can construct them empirically when sampling from a discrete and finite population. So notice that this construction is difficult when you have a large population, and it's also impossible with an infinite population. So to construct a sampling distribution, so we proceed as follows. First thing that we do here is, from a given population size n, we randomly draw all possible samples of size n. For example, let's say if the total sample has 20, then we are drawing all possible samples of size. For example, let's say the size of the sample is 4. So let's say there are 20 different waves, so 20 different values in the probability distribution, and we have 4 samples to take from each of them. How many can you take from that? You have, for example, if you take 4 from them, then we are basically taking all different versions of these samples. So let's say if you just have 5. If you remember, this is an example of permutations and combinations as well. Let's say if it has a total of 5, if your sample size is 3, let's say it is A, B, C, D and E. Then what are all the possible sizes that you can take of size 3? You can take ABC, you can take BCD, you can take ABC, you can take ACD, you can take ABD, ABC, ABE, and you can take ACE, ABC, you have ACD, you have ACE, you have ADE. These are all the possible ones that we can take. So this is an example of what we call sampling from a larger population. So we are basically taking multiple samples of different variations, and we compute the statistic for each different sample. For example, in each of these samples we are going to calculate the statistic of interest. For example, if it's the mean, we'll take for that sample, small sample, we'll take the mean of that sample, and we'll create a distribution of the means. So we'll call it the distribution of means of samples. So this term means of samples is refined and written as sampling mean. So this is the idea behind sampling distributions. So what are the statistics that we usually take? We generally need 3 things from a given sampling distribution. One is its mean, its variance, and its functional form, how it looks when you graph it. Now there are 4 types of these sampling distributions. One of them is distribution of the sample mean. Second is the distribution of the difference between the 2 means. Next, the distribution of sample proportion. Next, difference between 2 proportions. So these are all the ones that we generally take into consideration for sampling distributions. Now in a random sample of n measurements, so for a normally distributed mean with mean mu and standard deviation sigma, the mean of the sample is the same as the mean of the population. So the mean of the sample mean is the same as the mean of the population, but the standard deviation is also called as the standard error. So the standard error basically refers to the error in taking the difference between the sample and the population. So that is given by the formula sigma x equals sigma by root n. So we call that the standard error. So standard error is the square root of the variance of the sampling distribution, and we call that the standard error of the mean or the standard error. So it's written as sigma x bar, which can be written as sigma by root n. So this is the standard error or SE. Remember this one because you are going to use this over and over again. It is written as SE or SE underscore x bar. Both of them mean the same. Now, what do you do when you have non-normally distributed populations? So when the sampling is done from a non-normally distributed population, we use what we call the central limit theorem. What is the central limit theorem? So central limit theorem is the theorem that we use to convert non-normal distributions into normal distributions. So we are basically converting non-normal distributions into normal distributions. How do we do that? Is we consider the same as before from mean and sigma square, and this time we take mu becomes the same. So mu is equal to x bar is the same as mu, but here sigma square becomes sigma square by n. So sigma square x bar so becomes sigma square by n. So basically meaning that we are converting sigma x bar equals sigma by root n. Now, how do we calculate the z value here? So we know that z value, the formula is x bar minus mu by sigma, but sigma here is sigma by root n. So we can write it as x bar minus mu. So remember, x bar is the sample mean, mu is the population mean by sigma by root n. So this is the value that we take into consideration when we are converting. So this basically refers to the central limit theorem, CLT. So z equals x bar minus mu by sigma by root n. So the central limit theorem also implies the sum of n measurements when you take mu and sigma square by n variance. So when this n value is too large, we can approximate these distributions as normal distributions. So because of this, it allows us to describe the behavior and evaluate the reliability of these inferences. This is one of the reasons why central limit theorem is the most widely used statistical theorem in simplifying non-normal distributions into normal distributions. So if the sample is normal, then the sampling distribution of x bar will also be normal. Remember this point again. If the sample is normal, then the sampling distribution of that mean will also be normal. So what we are taking basically here, we are converting a skewed distribution into a symmetric distribution by using the central limit theorem. So when the sample proportion is approximately symmetric, the distribution becomes approximately normal. Now when the sample population is skewed, the sample size must be at least 30 for the sampling distribution to become normal. Remember this point again. So CLT, central limit theorem, only works when n is greater than 30. So central limit theorem only works when you have n greater than 30. Now remember that in the problems, if n is already given as less than 30, we can use the formula CLT directly. If n is less than 30, then remember that it must be mentioned that it is a normal distribution. Unless they mention that it is a normal distribution, do not solve it using CLT. So if the question says that n is less than 30, it must also be accompanied by the point that it is approximately a normal distribution. If they don't say that in that, then we do not use CLT to solve that problems. So this is how CLT solves the problems. When you start increasing the sample size, the number of samples, it starts making more and more symmetric distributions. So this is one of the reasons why CLT is one of the most widely used ones. How would you use CLT here? So here they are asking, given the information below, what is the probability that x is greater than 53? So they have given mu 50, sigma is 16, n equal to 64. Notice that n equal to 64 means that we can use CLT. Now they are asking you to sketch a normal curve. So this is the sketch of the normal curve. How do you convert the x to z value here? How do you find the z value? So the z becomes x minus mu by sigma by root n. So x here is 53. So 53 minus 50 by 16 by root 64. That gives you 1.5. So P of x greater than 53 becomes equal to P of z greater than 1.5. So we are basically finding this probability. So use the normal distribution table. So let me use the table now. So we want to know 1.5. So for 1.5 the value is 0.93319. So 9332. So this is when you have P of z less than 1.5 is 0.9332. So when you have greater than, so P of z greater than 1.5 can be written as 1 minus P of z less than 1.5. So that becomes 1 minus 0.9332, so which is equal to 0.0668. So this is the probability of x greater than 53. So let's try another problem here. Alright, so let's try and solve this problem. So what is given here? In a certain large human population, the cranial length is approximately normally distributed. So it's already given that it's normally distributed. Remember this point. With a mean of 185.6 mm and a standard deviation of 12.7 mm. So what is the random sample of size 10? Remember that n here is 10. Mean mu is 185.6 mm. Standard deviation is sigma. So sigma is 12.7 mm. They are asking you for the probability of x greater than x greater than 190. So we have to convert it into z-score. Notice that n equal to 10, it's less than 30, but it's given that it's a normally distributed function, so we can use CLT. So from CLT we know that z equals x bar minus mu by sigma by root n. So when you calculate x bar, so x bar here is 190 minus 185.6 over 12.7 by root 10. So pause the video and try to solve this one. So what will be the value now? You have so first find out 12.7 by square root of 10. So square root of 10. So you have 190 minus 185.6 by 12.7 by 3.1623. So when you calculate the value, so 190 minus 185.6 is 4.4. So that value gives you 1.0956. So this is that. Now round it off to 2 decimals. So 6 means that this becomes 6. So 9 becomes 1. So 1.10. So when you round it off, you get 1.10. Now using this value 1.10, so this basically becomes probability of z greater than 1.10. Again, so you have probability of z greater than 1.10, which can be written as 1 minus probability of z less than 1.10. So use the table. 1.1 is the value that we want. So 1.10 is 0.86433. So 1 minus 0.86433. So 1 minus 0.64486433 becomes 0.13567. So this is the answer for z greater than 1.0. So originally the problem is x greater than 190. So that answer is 0.13567. So this is the probability that at least 10 people will have more than. So in a sample size of 10, you have at least a 13% chance of having people who are greater than 190. So use the same principles here and pause the video right here and try to solve these problems. So let me write down the data that we have here. So there is they have given mean and the standard deviation. So mu is 120, sigma is 15. So both of them are in microgram per 100 ml, microgram per 100 ml. And they have given us the sample size is 50. So which means it's greater than 30. So we can use CLT. Now they are asking you for the probability that it's between 115 less than x less than 125. So pause the video right here and try to solve this problem. So if you're done with the last problem, try to use this problem and try to solve these problems one by one. So pause the video and try to solve these problems. If you're done with the last two, try these two problems as well. Next, let's go to the next one, which is distribution of difference of the two sample means. So this is where you have two different groups. So you have mu1, mu2, you have sigma 1 square, you have sigma 1 and sigma 2, and you have x1 bar, x2 bar, sigma 1x and then sigma 2x. So these are the two distributions that we do have. Now, how do you calculate the z value here? The standard error. So the standard error sigma x bar is given as under root sigma 1 square by n1 plus sigma 2 square by n2. Remember that we have two samples, separate n1 and n2. So we are comparing between the two samples. So here the mean mu x bar is going to be mu1 minus mu2. So this is the mean here, and the estimator value is x1 bar minus x2 bar. That's the value that we generally use. So this is the problem, and this is the formula for z. So z formula is x1 bar minus x2 bar minus of mu1 minus mu2 over square root of sigma 1 square by n1 plus sigma 2 square by n2. So this is the formula for z. So let's try this problem here. What is given in the data? You have population 1 with n1 equal to 40, x1 is equal to 346. In population 2, n2 equals 35 and x2 equals 300. And the variations are sigma 1 square equal to 2800 and sigma 2 square equal to 3250. Now what is the probability of obtaining the sample results x1 minus x2 bar, x1 bar minus x2 bar as large as those shown if there is no difference in the means of the population? So what they are asking basically is they are asking you to find probability of x1 bar minus x2 bar greater than 0. Now how do you find this? Basically put x1 minus x2 bar as 0 and try to calculate the z value. So what is the values given here? So n1 equals 40, n2, sorry, let me write down the n1 values. x1 equals $346, sigma 1 square equals 2800, n2 equals 35, x2 equals $300, and sigma 2 square equals 3250. So remember, why did we write this? They are asking you what is the probability of obtaining sample result x1 minus x2 bar as large as. So whenever you see as large as, remember that it's greater than, that there is no difference at all. No difference meaning that the difference between them is 0, between the means of the two populations. That's the reason why. If you see as large as, it means that is greater than 0. If you see as small as, then it is less than 0. So these are the two phrases that you will generally see in this chapter. Now using that data, write down the z value. So the z value becomes x1 minus x2, x1 bar minus x2 bar minus of mu1 minus mu2 over under root sigma 1 square by n1 plus sigma 2 square by n2. So here x1 and x2 are mu1 and mu2. So we don't need to write them again and again. So x1 minus x1 bar minus x2 bar is 0 minus of 346 minus 300 over square root of sigma 1 square is 2800 by 40 plus 3250 by 35. Now using this data, find the, so using this data now, try to find the answer. So using this data now, how do you find the answer now? So what will be the answer? So that z value will become 3.60. So I'm sorry, this is actually mu1 minus mu2 here is 0. So they are saying that there is no difference between the means of two populations. So mu1 minus mu2 equals 0. So this as x1 minus x2 will stay the same. Now, so based on this data now, what will be the z value? So 3.60. So they're asking for probability of z greater than 3.6. So that becomes 1 minus probability of z less than 3.6. Now let's use the standard distribution table. If you look at the standard distribution table for z less than 6, the value is 0.99984. So 1 minus 0.99984. So when you calculate, you should get 0.00016. So this is probability of z greater than 3.6, or the probability that x1 minus x2 bar is greater than 0 is 0.00016. So this is your answer. So use the same principles here and pause the video and try to write down this problem. So here they have given us the mean x mu1, mu2, sigma 1 and sigma 2. Sorry, this is x1, x2 and sigma 1 and sigma 2. And they are asking you for the simple random size is 50 for each of the population. So n1 is 50, n2 is 50, and you have x1 bar minus x2 bar. Sorry, so mu1 here is 183, mu2 here is 189, sigma 1 is 37.2, sigma 2 is 34.7. So in the question they are asking you what is the probability that difference between the two means xb bar minus xa bar will be more than 8. So they are asking you for probability of x2 bar minus x1 bar is greater than 8. Now if you flip this, because we know that x1 bar minus x2 bar is the general value we calculate, so the probability, if you want to flip this values, then just change the sign. So x1 bar minus x2 bar less than 8. So this is the value that you are calculating now. So pause the video right here and try to solve this problem. So if you're done with those problems, so pause the video right here and try to solve these problems. So with this we end lecture 1. So in lecture 2 we'll discuss the other two distributions.